This conference will now be recorded.
Okay, good evening, Deepa. We'll start now. We had started with the radioactivity part. So I'll just recap a little bit and then we'll learn few more things today. So give me a minute, just a minute. So the last class we had started with radioactive decay, law of radioactive decay. So we'll recap a little bit. Law of radioactive decay. So this law of radioactive decay we had derived that day, that if you have a radioactive nuclei and it starts decaying spontaneously, then after certain time t, you will have number of nucleus left in that particular substance. Suppose you have some 1000 nucleus, so all of them will not decay at a time. Okay, so the number of nuclei, if there are n0 at t is equal to 0, that means before it starts decaying, if this is the number of nucleus in that substance, after t time, what will be the number left in that? So that was given by law of radioactivity or law of radioactive decay. So this can be written as n0 into lambda into t e to the power minus lambda into t. So this is the number. Initially it was present at t is equal to 0. That means before it starts decaying, and n of t, this is the number of nucleus present in particular substance at any time. Okay, and what is this lambda? We had learned lambda is disintegration constant. Disintegration constant. Integration constant. Okay, I'll just. So what is the name of this? This is called disintegration constant. Disintegration constant. Okay, and see, another form of law of radioactive decay is given by the rate. So rate means R d n dt. Okay, this is the rate. In terms of rate, if suppose the decay rate, actually this means, if suppose a new uh, a new nuclear substance, it was decaying some 10 nuclei per second, okay, per second. This may not be constant always, because the decay depends on the initial number of nuclei. So decay rate also changes. So decay rate also changes in the similar way. So this was the rate initially at t is equal to 0, and this is at any time decay rate. That means number of decay rate means number of nuclei decaying per second into lambda t. And what is R0? R0 is lambda into N0. So this is what we have learned. Okay. So you must be thinking why you are recapping, because we will be using this formulas, both the formulae we will be using to derive two important time measurements or time, that those are half lifetime and average lifetime. These things will be deriving. Okay. So for that we need it. Before you go to half life and average lifetime, let us know the units of radioactivity. Unit of SI unit, mainly SI unit of radioactivity. SI unit of radioactivity. So SI unit of radioactivity is actually given by or the SI unit of radioactivity is becquerel. Becquerel. BCQEREL. Okay. So this is after the name of after the name of the inventor of radioactivity or discoverer of radioactivity, Henry Becquerel. Henry Becquerel. Now you have to know what do you mean by 1 becquerel. Actually 1 becquerel means it is in short it is written as BQ. Okay, so 1 becquerel is 1 decay per second. 1 decay per second. Excuse me. So this is 1 decay per second, and this 1 decay per second, this is in short written as DPS. You may get sometime this also. 1 becquerel means 1 DPS. Now this is actually the older unit of nuclear physics, older unit. So nowadays the mostly used unit is Curie. Okay, Curie. It is okay. So it is from by the name of Curie. Okay, you know the Nobel winner Madame Curie and Pierre Curie. So this is after the name of Curie. Okay, and say 1 Curie. 1 Curie. It is in short. It is written as CI also. 1 CI means 3.7 into 10 to the power 10 BQ or 3.7 into 10 to the power 10 DPS. Okay, so this is the SI unit of radioactivity. Okay, now we'll go to the next topic, that is the time measurement. So look, in radioactivity we know a nucleus. So radioactivity means spontaneous decay. Spontaneous decay. Okay, spontaneous decay of a nucleus. Okay, that is actually radioactivity. So since radioactive materials which has a tendency to decay out to its like different nucleus. So suppose you have some substance and you may have many nucleus. Okay, so how long it takes, how long how long how long the substance or all the nuclei take to disintegrate, all the nuclei take to disintegrate, or a substance nucleus, sorry, just a minute, disintegrate. So actually, to answer this, I'll tell you one more thing, that suppose you have been given a substance having N0 nuclei. So after how much time it will decay? Actually, this depends on the lambda. Okay, this depends on lambda also, initial number of nuclei, and also the decay rate, etc. So after what time the whole substance will be decayed, all the nucleus will decay. So these are the, like, this is the, now this is the problem, like how to find out the time when a particular substance will completely decay. So this time measurement can be done in two ways. Actually, there are two time there are two different types of time, different types of time which measures which measures sorry which measure how long a how long a given type of radio given type of radio nuclide lasts. So so there are two different types of time. So these will actually measure how long a particular nuclide will be lasting. Okay, we'll take a few examples later when we'll discuss alpha decay, beta decay, etc. And that time you see, if a nucleus, suppose uranium 238 92, it decays alpha particle and becomes thorium. Okay, thorium 90, and this is 234 along with alpha particle. Okay, so look, it is becoming actually a different nuclei itself, iridium to thorium. So that means if one nuclei decays, then we lose one nuclei from uranium. So like that, we'll be losing nuclei, nucleared, like after certain time interval. And then to decay all the uranium nuclei, if there are n0 number, to decay all of them, how long it takes? That depends on lambda, initial number, etc. But how to find out the time, how long it lasts? So to answer that, there are two different types of time measurements. Okay, two different types of time measurements. One is half life. So one is half life. Sometime half life time period also it says. Okay, let us keep it half life itself. Half lifetime or half life. Simply half life. So this half life, how to define this half life? Actually, half life it is the time. It is the time at which both n of t and r of t. You might be remembering what is n of t and r of t. See, we have defined here in the first. So this is the n of t and this is the r of t. That is why I recapped and wrote. Okay. So n is equal to n0. N of t means n0 into e to the power minus lambda t, and r of t means r0 into e to the power minus lambda t. Okay. Now, when so half lifetime is the time at which both n of t and r of t have been reduced, have been reduced to one half, one half of their one half of their initial values. Okay. So that is the time which is called half lifetime, and it is denoted by t half. Okay. Half lifetime is denoted by t half. All right. So see, we can find out a relation between t half and lambda. Lambda means disintegration constant. So this is important relationship you should remember to solve various problem in competitive as well as your board exam. So relation between t half and lambda. So we'll go with the definition. So we know, let us stick to this, n of t is equal to n0 e to the power minus lambda t. Okay, now according to the definition of half lifetime, what is that? That is n of t become that becomes n0 by 2 at t is equal to t half. Okay, so then from this equation what we can write here, n0 by 2, this is anyway n0, and e to the power minus lambda, in place of t I'll write t half. Okay, now from this equation, see here we can simplify a bit. So what we'll get, e to the power minus lambda t half is equal to half. Okay, if you just go for solving, like it will just remove the e to the power term. So for that you have to take anti-log, or both side you have to take log both side, and that is of e base log, so that means ln. So when you bring it lambda into t by half, it will be lambda ln half. So Then if you want to remove according to the rules of ln or log, we can write this. You look, we can write lambda into t half is equal to ln 2, and see t half will be is equal to ln 2 by lambda. So this is the relationship we know. But what is ln 2 of E base log? Okay, we'll write in the next page. Look, then t half is equal to, we have got ln 2 divided by lambda, and this has got a value, ln 2 has got a value 0.693 divided by, this is lambda. So this is the relationship between t half and lambda. And see, you have to remember this formula. If sometime lambda is given, you can find out half lifetime. If half lifetime is given, you will get the value of lambda using this relationship. Okay. Now we'll see another time measurement. So I had told you there are two types of time measurements. One is half lifetime, and another one is the average lifetime or mean life. Okay, average life or mean life, or mean life. You might be seeing mean life much more than average life in the question. Okay, so this is mean or average lifetime. You might be thinking, sir, why this average or mean lifetime? See, I have n number of nuclei. Okay, so you have a substance, you have n zero number of nuclei initially. So all of them has got some, like suppose if it is the same substance, so it has got a particular lambda. Okay, particular lambda. But one thing you have to remember, if you have n zero numbers of nuclei, it is actually a spontaneous process. This radioactivity is a spontaneous process. That means, let me take it some 100 nuclei. So all of them will not start decaying at the same time. That is a probabilistic case. This is a probability. Nuclear disintegration or decay is a probability. Like it is statistical probability. So all the nuclei may not start decaying at the same time. So if somebody starts in the beginning, somebody starts after 5 seconds, somebody starts after 1 year. If this is the case, all of them, even though they have same lambda, they may not decay. All of them may not decay at the same time. Okay, that means what? That means that means some nuclei may live for some nuclei may live for may live for live for shorter time period or shorter time, and some may live for longer time. Okay, longer time. From how to define this time? From the time when you start observing that, or measuring that. So that is the time. From that time onwards, or maybe you can say the time when they start decaying. Okay, all of them may not start decaying at the same time. That's why that is a statistical process. And because of that, all the nuclei may not last for the same year, same time. So some of them may live for longer time, some of them may live for shorter time. So this longer and shorter time. So to find out average lifetime, you have to take the time average of all of them. Okay, so look, this is the fundamental reason that we find out. We define a mean lifetime or average lifetime quantity. So this is the reason we have to define such a time period. Okay, mean or average life. Why? Because all of the nuclei may not decay or last for the same time. So how to how to derive this half lifetime? And here also, that means I am just okay. Let me define first what is average lifetime. So this is the time. This is the time So average lifetime is the time at which both N and R have been reduced to e to the power minus 1 of their initial values. Okay. Now we'll derive in the next page. We'll derive average lifetime. Average life. So to derive it, first of all, let us recall this law of radioactive decay, which we had written in the beginning itself. Okay. So you know each of the terms here. So the number of nuclei which decay in the time interval, the number of the nuclei which decay during the time interval t to t plus delta t. During this time interval, that can be obtained from the rate into delta t. Okay, rate into delta t. So this can be written again, lambda n0, that is r0, e to the power lambda t. This is r0. This is r0 into e to the power minus lambda t into delta t. So this is what is r of t is this term, and delta t is this. So if each of them has lived, if each of the nuclei, or let us write each of them lives for t times time t, then the total life, then the total life will be how much? That is, life will be see r of t delta t into t, because this is in during this time interval, this is the number of nuclei which are decaying. So what I said, average lifetime. So if you want to get the total time, like at which the whole nuclei will decay, is this one. If each of them live for t time, then this rate into, or so this is t into r of t into delta t. So which means t into, okay, n0 e to the power lambda t delta t, and along with that you have to multiply t. So this is the total life of all these nuclei. Okay, now as I said, if you want to get average, because some of them live for longer time and some of them live for shorter time, so to get or obtain the mean life, to obtain the mean life, we have to sum or integrate this term. Which term? Into delta t term for, or in between t is equal to 0 to t is equal to infinity. So you have to integrate or you have to sum over. So if we take delta t to be very small interval, then we can get that as in integration also. So if we get the total time means for all the nuclei. Okay, so look, so if I get the total time by integrating 0 to infinity, so this term again I'll write this lambda n0 e to the power minus lambda t into delta t. In place of delta t I'm writing, since I'm doing integration, I'll write dt. I'm just thinking that delta t limiting to 0, very short time period or interval. In fact, this radioactivity happens in fraction of seconds. Okay, so look, this is the total time for all the nuclei, total life for all the nuclei. So if you want to get the average, so you have to write the total number of nuclei also here, total number of nuclei. So that was present in the beginning, total number of nuclei. Okay, so this means this is, again I'll write this integration t into lambda n0 e to the power minus lambda into t dt, and over n0. So which means you can just lambda and n0, they are constant term, so you can stack this one and take this lambda out of integration, and see the integration is now this one. You have to do the integration of t e to the power minus lambda t into dt. So this is the term for which you have to do the integration to get the mean lifetime. Okay, now look, we can do the integration separately and then we'll write the final result. So 0 to infinity, I know you are expert in integration, so this integration, how we can do, we have to use by parts. Okay, by parts, integration by parts you have to do, by parts. So suppose this is I. So by parts, how do you do? Take this is the first function, this is the second function. So for the first function, what you have to do, you have to keep that as it is, and you have to integrate for the second function. If you integrate it, you get, this is minus lambda and e to the power minus lambda into t, and take the limit over here, then minus integration 0 to infinity. You have to take derivative of the first function, okay, then do the integration for the second function, e to the power minus lambda t into dt, and then finally you have to integrate it. So this term anyway, if you take this t is equal to 0, then also 0, and if you take limit infinity minus infinity, e to the power minus infinity also give rise to 0. So these terms will be 0. So first term actually contribute nothing to your average or mean lifetime. Okay, I hope you have understood why I'm striking this out to 0. So this will give you 0 because if you just use the upper limit, so t e to the power minus infinity, this will be actually 0. And if you take the lower limit, so t here, so t is equal to 0, 0 multiplied anything will be 0. So this term finally gives you 0. Here there is minus, and see if you integrate this term, you get minus lambda, so you minus 1 by lambda, and see this term ddt of t, that will be 1. So you get here minus 1 by lambda, so which makes you this plus 1 by lambda and e to the power minus lambda t. Again you have to integrate this term, so you get here, okay, so there is so you have to do it once. This is minus lambda t. Okay, so it will give you again minus 1 by lambda square, and this term you have to put the limit for, okay, 0 to infinity. So you will get value for the lower limit, so it will be actually 1 by lambda square if you see. So see, minus e to the power minus infinity will give rise to 0. Minus of e to the power 0 means 1. So you will get 1 by minus of minus 1 by lambda square. So this integration give rise to what? Give rise to 1 by lambda square. I'll just go to the previous equation. Look here. I have lambda into this integration. This integration I had taken I. So see, we have got this integration 1 by lambda square, right? So look what we get. Mean lifetime is given by 1 by lambda. So this is the relationship between mean lifetime and this is the so what is the relationship? So we get tau is equal to 1 by lambda. Okay, so this is the mean lifetime. So mean lifetime is actually tau means mean lifetime. Okay, mean lifetime, mean life, or sometimes it is written as average life, average life. Okay, so this is about average life and mean life. Now we'll learn about alpha decay and beta decay. We have seen that there are three types of decay. In the beginning, I had told you there are three types of decay. Okay, see, okay, I'll just go to this page and write the mean lifetime, mean life, that is tau given by 1 by lambda. So here now we'll learn. So there are three types of decay. One is alpha decay. Today we'll discuss alpha decay. Alpha, okay, let me write in words. Alpha means alpha particle. Alpha particle, what is alpha particle? We'll discuss that. So alpha decay. Alpha first of all, let us know what is alpha. Alpha is actually denoted by this sign, as you know, alpha, beta, gamma, delta, etc. So you have alpha. This alpha is actually a helium nucleus. Helium nucleus. This is helium nucleus. Okay. Alpha particle means helium nucleus. Nucleus. Okay, so this is alpha particle. This is called alpha particle. So what is alpha decay and when it happens? So during radioactive decay, this is a spontaneous process when a nucleus spontaneously decay by emitting alpha particle, that is called alpha decay. That is called alpha decay. What is alpha decay? When a nucleus spontaneously undergo decay of alpha. So when a nucleus undergoes alpha decay or undergoes a decay or undergoes disintegration integration by spontaneously emitting alpha particle, then it is called alpha decay. Okay, it is called alpha decay. So as I said, alpha is a helium nucleus. Okay, let us see if I suppose, see in this case, since alpha decay, or let me tell you, the alpha particle, let me repeat, alpha particle is a helium nucleus, right? So it has, see, it has Z2 and the mass number A is 4, right? This is the number of proton on electron. So suppose you have a nucleus which is disintegrating, that is called a parent nuclei. It is denoted by, you know, the composition, how to write for a nucleus. So this is called parent nuclei. Parent nucleus, okay, parent nucleus. This is called parent nucleus. Okay, parent nucleus. So suppose it emits spontaneously one alpha particle. One alpha particle means 2He4. Look, when it emits alpha particle, see, it is actually releasing how many proton? 2 proton, or Z will be reduced by 2. If the Z or the atomic number is changed, then the nucleus, this parent nucleus actually changed to some different nuclei. Okay, that does not remain the same nucleus. The property itself changes, so it becomes a different nuclei. Why? And and its composition can be written as Z minus 2, and mass will be written as, mass number can be written as A minus 4, because it is releasing 4 mass number and 2Z. Okay, so this will be the composition of the product, and this product is called, this is product nucleus, this is called, actually there are two product nucleus. So one is alpha, another one is this. So this is called daughter nucleus. This is called daughter nucleus. Daughter nucleus. And you see, daughter nucleus has different composition, and hence it is different than this one. I'll give you a simple example. Okay, I don't have page over here. I'll go to the previous page itself. So I'll just give you an example. Suppose uranium, it is a radioactive uranium 238 and 92. This is a radioactive nucleus, and it is supposed spontaneously decaying by emitting an alpha particle. So if I write alpha particle means alpha. I'll write simply alpha like this, or I can write this as 2He4 also. Okay, I can do both way. And see, the daughter nuclei will be actually thorium. Daughter nuclei will be thorium. And see how the Z changes. Z changes 92 minus 2. Okay, see, look here. Z changes by 2, like it reduced by 2, so it will be 90. So here it will be 90, and mass number changes by 4, reduced by 4, so 238 minus 4. So this will give you 234. So this is a completely new, even though this is also radioactive. So this is completely new nucleus than uranium. Okay, so this is called daughter nucleus, and this is called the parent nucleus. Now, one good thing you have to understand here, when, let us take this example itself. When such alpha decay happens, look, not only alpha decay just decay, just emit, but it emits with both the nucleus. This both are called product nucleus. These are called product nucleus. Both are called product or product nucleus. So both of them emit with certain kinetic energy. Even though this may be at rest, this may be at rest, but still these this two nucleus, they actually uh, emits or comes out with certain kinetic energy, and this kinetic energy is called, release of this kinetic energy is called Q value. I'll just tell you once again that this equation, see, this equation of alpha decay is not complete. Why it is not complete? Here, not only these two particles, here something else also releases, that is Q. Q means Q, it is sometimes called Q value. Q value. Q value means it is energy. It is having dimension of energy. Dimension of energy. Energy. Look, we have learned Einstein's mass energy equivalence is equal to mc square or delta mc square. Okay, delta mc square means what? If delta m amount of mass is getting vanished, that means this delta amount of energy will be getting converted to equivalent energy, that is given by delta m into c square. This is called mass energy. This is called mass energy. Mass energy. So in the alpha decay, what we have seen, suppose this is my parent nucleus. X is my parent nucleus. X is parent nucleus. Z, and this is A, and it is releasing alpha particle. This is 2He4 plus daughter nucleus, that is Z minus 2, and this is A minus 4. Okay, along with that there will be some release of energy, that is called Q, or sometimes it is called Q value. Mostly it is called Q value. So what is this Q value and how this energy is getting released? Look, in this case, if we see, this nucleus has mass, suppose mx. This has mass alpha, I write m alpha, and this has mass my. Now, if you take the difference of this mass, difference of masses, let me write it, then you will be able to understand better. if you take the difference of this mass, that means you have parent nucleus mass mx, and just you have mass m alpha plus my. This is the product. This is the parent and this is the product. If you take the difference, you will see that this mass, actually if you just sum the mass of alpha particle and the daughter nuclei, that total mass will be actually less than the mass of the parent nucleus. And see, this will not be delta m, that's why delta m will not become 0, because this is actually because mx is greater than m alpha plus my. So there is a mass difference between the parent and the product nucleus. So where will that mass difference go? Will that disappear in the oblivion? No. It will actually get converted to mass energy. Okay, that will convert it to energy. As I said, according to Einstein's mass energy formula, it will be converted to energy, and that energy actually will be shared by the daughter nucleus and the alpha particle in terms of kinetic energy. So that's why the alpha particle and the daughter nucleus, they will actually get released with certain kinetic energy because of this Q value. And what is Q value? I'll write now again. What is Q value? This is the delta m c square. This is the difference in the mass of the parent and the product nucleus into c square. So this will give rise to Q value. This Q value for different uh, reactions or for different elements decay, alpha decay, will give rise to different Q value. And this Q value, this is energy actually, okay? So this is energy. This is even called mass energy also, energy. And this energy will be shared by, this energy will be shared by, will be shared by the alpha particle and the daughter nucleus. Okay, daughter nucleus. Okay, so that's why, and this energy is shared by this as kinetic energy. That means even if the parent nucleus X is at rest, but these two guys will come out with kinetic energy. Kinetic energy. This alpha particle and the daughter nucleus, they will be produced with some kinetic energy. Okay, so I'll stop it here today with this. Then next day, if I start beta decay, then it will go again another 10 minutes. I don't want to go. So we'll learn beta decay and gamma decay next day, in the next class, Wednesday, and we'll take up few numerical examples related to alpha decay, beta decay, gamma decay, etc. And also we'll take few numerical problems on average lifetime and half lifetime on Wednesday. Okay, so Deepa, if you have any doubt now, you can ask me related to what we have learned today. Mean lifetime, average lifetime, then this alpha decay, etc. And the derivations I had done elaborately. If you have any doubt in those, you can ask me now. Is there any doubt, Deepa? If no, then I'll stop it here. We'll meet again on Wednesday. So bye for today.